Hello and welcome to this webinar on solving complex nonlinear problems with SIMULIAworks. I'm John McCready and I'll be your presenter for the next 30 minutes. So what is SIMULIAworks? What can it do? Where does it fit in our portfolio? And ultimately, how can it help you solve these complex problems? SOLIDWORKS simulation takes a scaling approach to accessing capability. This allows us to offer the most appropriate tools for a particular job. For example, Simulation Standard allows users to guide designs by performing stress, fatigue, and motion analyses. Simulation Professional builds on this by offering further procedures to understand thermal behavior, local and global buckling, and to extract frequencies where needed. There are even tools to review and maximize the performance of your design using topology optimization. Simulation Premium again adds to this, offering nonlinear procedures and the capability to perform dynamic events and understand composite behavior. For domain experts, there is also SOLIDWORKS Plastics and Flow. Plastics allows users to simulate the forming operations and interrogate their tool design to ensure that the final product matches their original. Flow allows users to look at both internal and external flow, as seen in electronic cooling and HVAC systems, and it can do much more. And all these tools are accessed on your desktop through the intuitive SOLIDWORKS interface. However, as part of the Dassault Systems family, we are now able to access further simulation capability through SIMULIAworks. Simulia is known cross-industry and worldwide for their robust solutions to highly complex problems, and we can access this functionality through 3D Experience platform on the cloud. The 3D Experience platform is a managed, secure way to access the applications you need to perform particular tasks. These could be meshing some geometry or preparing it for a simulation by doing some simplification. These applications are packaged in roles that allow you to perform job functions such as creating and analyzing simulations. Users can have multiple roles depending on their function within an organization. You could be a team of one with many roles, or you could be a team of many with a single role. SIMULIAworks roles allow us to extend into analyst level problem solving. And continuing the philosophy of scalability, there is structural performance engineer, and this role leverages the Abacus standard solver to perform analyses of static and dynamic events. These could be simulating manufacturing processes or looking at operational loads. Extended on that, we have structural mechanics engineer. It has the same functionality as structural performance engineer, but it has more procedure types and also brings the Abacus explicit solver to the table for those particularly troublesome problems. This is particularly useful when dealing with crushing, rapidly changing contact interactions, and drop test scenarios. Both these roles have access to expert-level meshing apps, an enhanced element library, including hexes, and the ability to accurately model material behavior, even into damage. But we also have access to other roles, such as simulation collaborator. This is for those who may not create or modify simulations, but they could be stakeholders or domain experts on a particular problem or project. They're more interested in reviewing the simulation data, doing comparisons, sharing their knowledge, and collaborating with the team members. Taking a step back, we can see where SIMULIAworks is positioned based on a problem's complexity. For SOLIDWORKS simulation users, it offers a solution to problems that are currently not solvable, problems that take a significant time to solve when you want a performance gain, or problems that require advanced tools. Perhaps you need more meshing options, more control, more robust contact, or access to more material models. Maybe you're analysing hyperelastic rubber seals. In this way, it can be seen as an extension. However, SIMULIAworks requires no SOLIDWORKS install to work and can be an alternative for simulation users who regularly deal with complex problems. So what makes a problem complex? Surely the list is endless, but let's see if we can highlight the major contributors. And let's start with a product's design. Complex geometries and material selection may require access to deeper mesh controls and element formulations to accurately model a virtual representation. The scale of the problem can exponentially impact complexity. Are we looking at nuts, bolts, or a full component? Perhaps we're looking at large assemblies built from multiple sub-assemblies and components. Are we interested in interactions between these? The manufacturing processes are also important, particularly if these are the events you're simulating, be it forging, forming, riveting, or whatever. Or perhaps you're more interested in the post-process behavior. Do you have any residual stresses, for example? And what will they impact? You will also be interested in how the product will perform in its usual or extreme operating conditions. Do we need to include thermal as well as mechanical effects? And the last form of complexity that can be easily overlooked is collaboration. You can have a simple problem, but if the solution involves disconnected tools and people, it can very quickly become complex due to out-of-date information, miscommunication, or a loss of accuracy moving between tools. For now though, let's take a look at how nonlinearities can impact our simulations. There are three main forms of nonlinearities. Geometry, where large deformations can cause a change in shape and ultimately a component stiffness. Material, where we are operating outside of a linear relationship for stiffness. And boundary, where we have changes happening due to contact interactions, be it component to component or self-contact. Let's take a deeper dive into each of these and highlight where solutions exist. Depending on the problem, it is possible to ignore geometric nonlinearities. However, doing so does require an understanding of the problem at hand and the scale of any expected deformations. A linear approach assumes that we'll only see small deflections, small rotations, and small deformations during our analysis. However, in reality, a structure's stiffness will change as it deforms. So it becomes a case as to whether the nonlinear effects will be significant to decide if they should be excluded. Another reason to exclude these effects, or if a trade-off can be made in result accuracy for performance. In cases where the behaviour to loads is not fully understood, as in many analyses, it is more realistic to incorporate the potential for nonlinear geometric effects. This allows us to deal with dramatic changes in shape whilst retaining accuracy to real-life events that we are simulating. As shown in this high-performing example, there's a lot of motion in the mesh as it's subjected to these pressure loads, and we are able to capture these large deformations without hassle. With SIMULIAworks, we're able to capture these realistic responses in our virtual testing for simulations involving large deformations, both static and dynamic in nature, buckling to understand global and local behaviour, and in preloading, where interactions between gaskets, for example, and bolt loads can highly deform a structure locally. Now let's talk about material nonlinearity. How we define our material's mechanical response will depend on the experimental data available and the operation or event we're simulating. If we understand the loads and their associated strains are small, we may be able to simplify our analysis and assume we're operating in the elastic region of our stress strain curve. As to how long this could be assumed to be correct will depend on the material and the load history. As we move beyond this elastic limit, we start to see a non-linear relationship forming, which can significantly affect the structure's response to increasing loads. We are inducing plasticity in our structure and will not see a return to our original shape even if we remove the load. This can be an area of concern for part operation, or it can be by design in manufacturing processes such as cold forming. Here we see a component driven through tools to generate our desired final product shape. SIMULIAworks allows users to define metal plasticity based on the Mises or Hill yield surface, allowing for both isotropic and anisotropic yield. Temperature and rate dependence can also be included within these definitions. As strain rates increase, many materials show an increase in their yield strength. The effect becomes important in many metals when this strain rate range is between 0.1 and 1 per second, and it can be very important when they range between 10 and 100 per second, which is very characteristic of high energy dynamic events or manufacturing processes. Depending on our material, we may see a yield as a single transition. However, we may also see yield regions with distinct upper and lower yield points. It's important to understand this mechanical response, particularly when investigating strain hardening effects during manufacturing processes. Here we can see a multi-step metal forming process, which relies on an understanding of not only when we see plasticity, but also whether any hardening effects are taking place. With SIMULIAworks, we are able to model not only isotropic hardening, but also kinematic hardening when witnessing cyclic loading. If our structure is likely to experience high loads, such as in extreme operational conditions, it may begin to move towards its maximum strength. This could be driven by mechanical or thermal effects. Is the product operating in intense heat or beyond its designed limits? The more data we have, the more data we can incorporate, the more accurate the response we get. This allows us to more fully understand a product's capabilities before it has been constructed or physically tested, allowing for a significant reduction in the design cycle time. This can also aid in designing a product to optimally meet objectives. For example, this could allow a design with reduced mass in high stress concentration areas driven by your simulation understanding of how much abuse the structure can take. As we move beyond the material's maximum strength, we will see a loss in stiffness. As such, we could simply use a failure measure and stop here. However, with SIMULIAworks, we can go further. We can define whether and when damaging behaviour initiates and how it evolves during our analysis. There are a number of options available for this. For ductile materials, one method regards this onset of damage based on the nucleation, growth and converging of voids. There are others. The evolution of damage can then also be defined based on displacement or fracture energy, with softening options available. This allows us to visualize the destruction of products due to increasing loads and even ballistic impacts. We can also deal with non-metallic materials, such as composites, hyperelastics, viscoelastics, and hyperfoam, to name a few. For hyperelastics, we have a greater selection of material models to more accurately define your given product. These include the basic neo-Hookean approach, with further models available, such as Yao, Marlowe, Ogden, Arruda Boyce, and Mooney-Rivlin. Selecting the appropriate model from experimental data is made easier through use of the material calibration app packaged with Structural Mechanics Engineer. Boundary nonlinearities occur when loads or restraints change as a response to structural deformation. These can be due to changes related to contact interactions, such as moving from a sticking or slipping condition, or the opening or closing of normal contact surfaces. With SIMULIAworks, we're able to model complex behaviour for each of these situations. We can deal with anything from frictionless to rough behaviour and anywhere in between. For more realistic responses, we can directly define these relationships and base them on the current normal contact conditions, even incorporating rate-dependent effects. For normal behaviour, we can define conditions for self-contact, interactions between components, and sticky contact is also a possibility. In thermal or thermal structural analysis, we can define the conditions for gap conductance. All these tangential and normal relationships can be defined at a global, component, and even surface levels for maximum control. Follower forces are another form of contact nonlinearity, where the load direction changes based on a deforming structure. Here this is visualized with an incredibly low quality video of a blow molding operation on a bladder. As the bladder expands, the load direction changes across the evolving surface, and we're able to manage that. So that's the three main forms of nonlinearity. Wouldn't it be great if they never impacted each other just to make our lives simpler? Unfortunately, that's not the case. We'll see complex relationships between these during the load history. In this example, we see an elastomeric keyboard dome that you would find in many keypads. There's geometric nonlinearity in the form of large deformations and both global and localized buckling, as seen in the structure and the legs. There is also material nonlinearity as we're looking at a silicone rubber utilized in a hyperelastic material model. And finally, we have a lot of boundary nonlinearity as the structure contacts the floor. It should be obvious why incorporating these effects are important to fully understand and simulate a realistic response. Moving back to our conversation on complexity, let's take a closer look at some of our contributors, their underlying challenges, and if any other solutions exist within SIMULIAworks to combat these. So let's take a look at a product's design. A major challenge with a product's design is that it can and will change many times before production. As such, having tight integration or associativity between CAD and simulation tools can be beneficial in achieving these rapid design cycles. With SIMULIAworks, you have associativity with SOLIDWORKS Desktop and SOLIDWORKS Cloud roles. You're able to push a design change to your simulation model with one click. The simulation model can then be updated if any changes are needed, or simply rerun based on a new design. The Managed Data Model on a 3D Experience platform also allows for parameterized CAD and simulation features for quick modification during methods development. For example, these parameters can be linked to mesh densities on certain structures, so the user doesn't need to navigate a large product structure, the meshes, the finite element models, just to make a small change. They can just access these parameters and quickly change the model with an update. The scale of the problem, from parts, sub-assemblies and assembly, means solver robustness and compute scalability is essential for full understanding in an acceptable time frame. With SIMULIAworks, you can solve locally or push your simulation to the cloud to leverage further computing power for increased performance. In these cases, you'll be provided with estimates to understand how your licensing pool will be affected by a cloud solve. When dealing with larger structures, contact can become more important. As such, you may need to balance the time to configure these contacts with the time they take to solve. Here you have the choice to define contact relationships using either a top-down general contact approach, where everything may contact anything at any time, or define contact based on a bottom-up approach specifying contact surface by surface. Both methods are robust and accurate and can be used together to quickly define these component-to-component or self-contacting relationships. As stated before, we can define multiple contact properties that can be reused to reduce configuration time and increase productivity. The product's design and the scale of the problem being analysed can also require differing levels of mesh control to best conform with geometry and achieve the required results accuracy. There is a wide selection of 1D, 2D and 3D meshing algorithms available to the user to define the discretized nature of the structure. You can define beams, shells using quads and triangles, or solids using hexes, tets and pyramids using these algorithms. These algorithms offer differing levels of surface conformance and performance trade-offs. The user interface also takes a designer-led approach, allowing users to delve deeper into the mesh controls as their skill levels increase. Recommended defaults can then be modified based on the user's experience. And another added benefit of the managed data model is that any mesh specification a user creates can be saved as a meshing rule. These meshing rules can then be searched for in the database and reused for other components or simulations when similar geometry is encountered. And that could be reused by the same person who created it or another person who has been provided access to your platform. A perfect example of knowledge capture and reuse across an organization. Manufacturing processes can be multi-step dynamic operations. They can involve material manipulation or the connecting of components through many means. With SIMULIAworks, we're able to simulate a suite of connections, from general ties and couplings to simulating virtual bolts, welds, and general connectors. These general connectors can be based on templates, or they can be defined by the user for a complex relationship. Connectors can be defined with their own rigid, elastic, or nonlinear properties to accurately simulate a real connection while minimizing computational expense. We've already spoken about the collaboration between tools, so what about people? With SIMULIAworks, we have access to roles and applications that offer the ability to share live results from our simulations, which is important when relaying to stakeholders or customers, manage the life cycle and state of our data. For example, we can create a new version of our simulation on the go. We can also review content, whether it's posts, comments, images, documents that contain specifications or requirements, and 3D models that are on our managed platform. We can also communicate and collaborate in user communities. And this offers us full traceability on decisions made and allows us to have team members collaborate in a live fashion. And this is all possible through 3D dashboards and 3D Swim on the 3D Experience platform. And these tools are accessible through an internet browser, which allows everyone to operate in a connected fashion across teams, companies, and borders where required. We've talked about what makes a problem complex and delved into a number of major contributors, not all related to simple feature function technical solutions. We've explored nonlinearities and what effects they can have, and why a nonlinear approach can be beneficial to generate more realistic and comparable responses, be it to experimental results for validation or to real-life findings for direct comparison. We've even highlighted some capabilities across the SIMULIAworks roles and applications to meet particular challenges. We now have a portfolio that covers a greater range of problem complexity, offering a guiding hand to designers whilst also allowing expert analysis, the tools and depth to perform complex analysis and optimize a product's performance. Native SOLIDWORKS simulation offers a considerable selection of tools for analysing structural applications as well as flow and plastics, all on your desktop in the familiar SOLIDWORKS interface. But now, should you ever need advanced simulation tools, be it to complement your current SOLIDWORKS install or as your main simulation solution, SIMULIAworks rules are something to investigate. The structural rules I've covered all leverage the well-known abacus solvers to deliver results faster and offer more capable, more robust solving. With SIMULIAworks, you define your simulations locally and manage your data through the 3D experience on the cloud for maximum accessibility and added security. As a platform solution, you have the added benefit of all data being managed. This allows you to see who created the content, when it was last modified, what state it's in, and whether or not there's any content linked to this, be it documents for requirements or whatever. For large problems, cloud compute can also be used to improve turnaround time and reduce hardware overhead. The Simulation Collaborator rule allows a user to leverage data management, finding the content they want when they need it, all through an internet browser. And they're able to review results on the go, which could be beneficial when presenting results to a stakeholder or a customer during a meeting. You'd be using live results rather than a week-old report. It also allows a user to inform decision making, performing performance trade-offs to identify the best product from a selection of designs. And they're able to collaborate with other users to rank requirements and objectives based on performance. This allows you to retain full traceability, ownership, and capture best practices to reduce future design cycles. In terms of simulation creation, we start with Structural Performance Engineer. This offers the capability to perform general static steps, quasi-static steps, and fully dynamic steps using the implicit abacus solver. You're also able to perform static perturbation steps, looking at buckling, extracting frequencies, and looking at harmonic response and modal dynamics for things such as suspension systems going over rocky roads. If heat transfer is of interest, you can perform both steady state and transient heat transfer steps. You can perform these solo or as part of a sequentially coupled thermal structural analysis. In order to ensure beginners can understand the tools, there's a guided workflow that details what the different tools are, what they do, and whether or not they're required for the simulation in question. Meshing takes a beginner to expert approach, only requiring the user to delve down to the controls based on their experience. The default recommendations will suffice. In terms of post-processing, you can interrogate contour plots and create history plots, and you can look at key locations using sensors. There's also other tools available, such as creating reports based on templates. Should you require more capability, either to get a result faster, or perhaps you've got a lot of complexity in terms of contact and nonlinearities, and where inertia becomes important, you want to think about Structural Mechanics Engineer. This is all the capabilities of Structural Performance Engineer with some added procedures. You're able to run random vibration steps as well as complex frequency, and now you've also got access to the abacus explicit solver for those highly dynamic events. You've got all the same expert meshing and post-processing tools, but now you also have access to the material calibration app. For example, if you're analysing a rubber seal and you want to select the best hyperelastic material model, you can take your experimental data, use the material calibration app, and identify what is the best material model for your analyses. And you're also able to restart analyses. So if you want to add a subsequent step after you've got a solve, you can do that. And there's also extra geometry simplification tools. So to summarize, what can we solve with SIMULIAworks? We can solve large deformation problems, multi-step processes, whether it be from manufacturing or some real-life event. We can deal with complex contacts, whether or not it's open and closing, sticking and slipping. We've got a lot of different options available for these. We can deal with preloading, for example, bolt connections. We can do snap fits. and we can perform spring-back operations after we perform a forming operation. We can also perform thermal analyses, either solo or sequentially coupled with a structural analysis. And we can also look at highly dynamic tests such as drop tests and impacts, perhaps involving ballistics. And the list is endless. Hopefully I've hit on topics that resonate with you and highlight key technologies accessible with SolidWorks and SIMULIAworks. I'd like to thank you for joining this webinar, and should you have any more questions or interest, please contact our team or your local SolidWorks reseller. And lastly, happy simulating.